In this video, I want to talk about how to actually get the wave function for our case where we have spin from the state that is, say, a spin state. So if you remember, the way to go from a basis state or some general vector state to the wave function is to project it onto a basis state. So if we started with some state psi, then we can get the wave function psi of x by basically making the product of x with that state psi. So before we did it with just coordinates, x, y, and z. Now we want to incorporate spin as well. So in this case, what we would have is our state, and I'll make it capital psi. And then what we want to do is project on it x, y, z, and sz. So we have the Cartesian basis x, y, and z, and then we also have the basis for the spin, at least the spin projection in the z direction. And if we make the product with our vector space like this, then what we should get is a wave function in coordinates x, y, z, and spin, which is basically this vector, which is a projection of the wave function when it's spin up, x, y, and z, and the wave function spin down as a function of x, y, and z. So really, we're creating the spinner. We're creating a wave function which is a spinner. How would that work if we wanted to normalize this wave function? Well, if we normalize it to 1, that's, we sum up of all probabilities, which includes the probabilities of x, y, and z, but also the probability including the spin projection. So that would be the product of the states psi with itself, which is equal to the integral over 3 dimensions, x, y, and z, the wave function psi, x, y, z, and spin, basically psi star psi, the wave function times its complex conjugate. So that's x, y, z, spin z of the state psi, integrated over x, y, and z. But we also have to sum over the two possibilities of spin up and spin down. So we'd also have a discrete sum over those spin states, spin up and spin down, which is basically taking the vector product. So in the end, when we take the product of all possible spin states, we would still get now the integration over all Cartesian space, but then we would get the amplitudes of spin up squared plus spin down squared, and then you integrate over those wave functions dx, dy, dz. So it's just an added twist now that we're using spin, is that you have to get this this product, which turns out to be a vector product. It's basically like taking the Pythagorean theorem and applying it to our two components, spin up component and the spin down component. Operating on this spinner with some, so given a general operator, which we haven't defined, we'll just call it capital omega. So capital omega operating on the state psi, remember, is actually a matrix operator. So it would have to, the psi would have to operate on both the spin up and the spin down components. So you basically have this 2 by 2 matrix, which is basically a diagonal matrix, where it now can operate on this spinner, like so. Now, I've just been talking about very generic topics of functions. I haven't defined any of our wave functions. I haven't defined really any of our spinners. I haven't based it on anything physical, except to say that quantum mechanics has to treat spin as a vector of wave functions. It turns out spin can be completely separated from the Cartesian coordinates, and so this basis x, y, z, and spin, I should be able to write this as the state x, y, and z, and a union with the state that is the spin. Just like x, y, and z are orthogonal to each other, so we could break them up into a union of these three one-dimensional bases. We can also break it up into x, y, and z is all of the translational and orbital stuff. Or the rotations. And this is just the basis for spin. So in the end, we've already solved a bunch of problems in x, y, and z. So, we've done 3 dimensions in spherical coordinates. We've done the radial equation given the Coulomb potential for a hydrogen atom. So we don't have to redo any of that stuff. That stuff is already done. Now what we have to do is work on the spin, and since the spin basis is basically independent of the other space, then all we have to do is write down, let's say, the state chi sub s, so basically the spin basis, which is the basis for it would be the total spin and the spin projection. So just like orbital angular momentum, where the two components that were most important were the total angular momentum and one projection, we usually chose z. But since angular momentum in the x, angular momentum in y, and angular momentum in z are not good quantum numbers together, the good quantum numbers, the ones that commute, are the total angular momentum squared and one projection. And we chose z. Same thing will be true for spin. We just need to label the state with a total amount of spin and a projection of that spin, which we can rewrite as the total spin and then a quantum number m sub s times h bar. That's the eigenvalue of it. So I can rewrite this then as h bar s m sub s. So now we can write our states in a spin basis where, like, say for the electron, which is a fermion that only has 2 spin projections, spin up and spin down, I can write this basis as either total spin of 1/2 and then a positive spin of 1/2, or a total spin of 1/2 and a projection minus 1/2. So spin up, spin down, projections. Now I could write my state, chi, as a superposition of the two possibilities. So some normalization alpha times the spin up state plus some normalization beta times the spin down state, like that. The normalization for this would be basically the product, which gives me basically alpha, the spin states 1/2 minus 1/2 are orthonormal, so they normalize to 1. And it's just this normalization that we have to worry about. So you get the product of the complex conjugate of the state, basically this one right here, the bra, multiplied by the ket as vectors. And so in the end, what we get is 1 is equal to alpha squared plus beta squared. Which, basically a good choice of that is either plus or minus 1. So in the end, if we wanted to make a transition from one spin state to the other, we could make the product of spin 1/2 going to either a plus or minus, so going to a spin up or a spin down. We project out the z component on a state that has a total spin of 1/2 and a projection of either spin up, plus or minus. And so when I operate with the spin projection operator on these states, I'm going to either pull out the 1/2 or I'm going to pull out the minus 1/2. And so the eigenvalue is either plus or minus h bar over 2. And then since this is z, it's in the z direction, the k hat direction. So I could generalize this even further by saying, let's consider just any direction, x, y, or z, and I might call it a direction vector, a directional vector. So it's basically like a unit vector. So now what I have is n hat plus or minus. I'm operating with the spin on this state. And what it gives me is plus or minus h bar over 2, that direction, whether it be x, y, or z. So, what if we think about this in terms of angular coordinates? What are the directional vectors in coordinates of theta and phi? Well, n sub x is sine theta cosine phi. N sub y is sine theta sine phi. N sub z is cosine theta. And so now I can write out the product of, the direction times the spin, which is n sub x sx plus n sub y s sub y plus n sub z s sub z. And so this product becomes, well, from all of the spin operators, I get h bar over 2, and from the direction, the spin operators plus that matrix for s sub x, which was 0, 1, 1, 0. So in this case it would be 0, n sub x 0, plus h bar over 2, 0, minus I, ny, 0, plus h bar over 2, n sub z, 0, 0, minus n sub z. So then if you put that all together, you get h bar over 2, n sub z, nx minus I, ny, nx plus I, ny, nz. And if you plug in those functional forms, what you get for this particular case is cosine theta, sine theta, e to the minus I phi, sine theta, e to the plus I phi, minus, because there's a minus sign in there, cosine theta.